All right, folks, we're going to get started here in section 11.2. I'm breaking section 11.2 into two parts. There's a lot going on in section 11.2. And we're going to start to see why we did everything that we did in chapter 10, why we learned all of those series, all those tests. It all starts to come out here in section 11.2, which is power series and properties of power series. So this is part one. So far, folks, we've studied series of the form, well, just series A sub n, where each A sub n was a number. In other words, we've just looked at series of constants, numbers, adding up numbers. So that's basically arithmetic. We're going to now generalize this arithmetic and consider series of functions. This means we are going to start to see the variable x in the series. And we're going to formalize this idea in the following definition of power series. So here it is, the definition of a power series. Suppose x is a real variable, then when you have an infinite series that looks like this, the series n equals 0 to infinity, a sub n, x to the n, and I've written down some of the first few terms of the series. So the first term is a sub 0 times x to the 0. Well, x to the 0 is 1, so that's why the first term is just a sub 0, plus a sub 1 times x, plus a sub 2 times x squared, plus a sub 3 times x cubed, plus yada, 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 plus a sub n x to the n, plus yada, yada, yada. That general form, that's what we're going to call a power series. Now I'm going to put down an even more generalized looking power series. And here's the more generalized looking power series. Rather than just having an x to the n, you have the quantity x minus c to the n. And in that form, we say the power series is centered at c. And c is just a constant, a real constant. So in the first one that I wrote down here at the top of the slide, that fits the more general form, where in the more general form, c would just have a value of 0. Folks, it's dreadfully important. You must think of a power series as being a function of x, f of x. You have to think of a power series as being a function of x. I mean, I'll write it down that way. Think of f of x equals the series n equals 0 to infinity a sub n x to the n, or the f of x equals the series n equals 0 to infinity a sub n x minus c to the n. We have to start thinking of these power series, since when we wrote them out term by term, we did see, x appearing quite often. So think of it as a function of x, where one, f of x is the actual sum of the series, whatever that function is. The domain of f of x, whenever we talk about functions, we always talk about domain of functions. The domain of f of x is the set of all x for which the power series converges. And then look at that definition again. When you look at the term by term, when we wrote out the term by term of the power series, that function kind of reminds me of a polynomial function. Well, except there's an infinite number of terms. So let's look at an example. This is a classic example of a power series. In fact, this one I'm going to put down is going to be incredibly important. The series n equals 0 to infinity x to the n over n factorial. And I've written down the first few terms of this power series. Trust me, we are going to see this power series later on. We are going to discover what function this power series is equal to. And it's going to be something that I'm going to suggest you just file away into your memory banks, and you know what function this equals to. It'll pay off possibly in a differential equations course that you'll take in the future. Note that this power series, note that it's centered at 0. And, well, look, folks, this is a 3-star comment, and I put it in bold. Our game in this section, and, well, what we're going to do here in Chapter 11, our game is to determine for what x's a series such as this converges. In other words, find the domain. So we're looking at this and we're thinking, what numbers can we put in for x so that when we put a number in for x, we would get a series of constants that converges. So for example, if I put 2 in for x, I would get a series of constants. Does that series of constants, does it converge? So that's what our goal is. For what x's can we put in, for what numbers can we put in for x and get a series of constants that converges? And one more thing before I go here. If anyone's kind of worried in my series representation, when I wrote term by term, that I have a 1 plus x squared over 2 plus x cubed over 3 factorial. And if anyone's wondering, well, Bill has a typo here. That denominator of, x squared over 2, that denominator should be a 2 factorial. I didn't bother with factorial there because I know 2 factorial is 2. So don't worry about it. Let's look at another example. Consider the series n equals 0 to infinity, x to the n. So here's the deal with this one. There's a lot going on here. So I'm going to head off to the board to discuss this one more in depth. There's some pretty cool stuff that's going to fall out of this one series. So let's head to the board and see what the deal is. All right, hey, this was that example I said I wanted to talk a little bit more about on the board. You were given the series n equals 0 to infinity x to the n, and I wrote down some of the terms of this power series. The first thing that I want to note is that the power series is centered at 0. So I'll make that little note off to the side here. It's centered at 0. Okay, the other thing that I think is kind of cool about this particular power series is look at it. It's x to the n. Doesn't that remind you of a geometric series? And remember, the geometric series was the form a times r to the n. I could say a is 1. Doesn't it look like a geometric series? In fact, it looks like a geometric series where r has the value of x. So now think about this. It is a geometric series. And we know for a geometric series, we have absolute convergence when r, the absolute value of r, is less than 1. Well, it just looks like x is in place of the r, so I just put x in place of the r, and we know this absolute value inequality can be rewritten as that compound inequality. Folks, you have just found the domain of this power series. You pick any x that's in this interval, say 1/2. Pick x equals 1/2. Put 1/2 in there for x. You have the series 1/2 to the n, which you know is a geometric series. It's a series of constants that converges. Pick 7/8. That's in the interval. Put 7/8 in for n, or in for x. You have the series 7/8 to the n power. That's a series of constants. It's a geometric series. You know it converges. 1 is not in this interval. And think about it. If you were to pick 1 and put it in here for x, you have the series 1 to the n. That diverges. Fails the nth term test. Pick another x that is not in this interval. Say, I don't know, 3 or 18 over 5. Put that in here for x. 18 over 5 to the nth power. That's a geometric series that you know diverges because that r is larger than 1. So folks, this is the domain. It is the domain for this series. Which is kind of cool. For this series, because it's a geometric series, you're able to determine the domain. You're able to determine all values of x where this beastie converges. But there's one more thing that I think is really cool. You know, with a geometric series that converges, you know the formula for the sum is a over 1 minus r. You know that. So you know that this series that is geometric, you know where it converges, for what values of x it converges, its domain. You know what the sum of this series is. And you know this series sums, thanks to this formula, knowing this formula for the sum of a geometric series. Well, a is 1. 1 minus r is x. This function, 1 over 1 minus x, is equal to this power series, as long as you're on the interval -1 to 1. For that domain, -1 to 1, they are exactly the same. That's kind of cool. I think that's kind of cool stuff. And here's what we need to do now. We need to head back to the slide. I need to introduce a little bit of vocabulary, and so let's see what that's all about. So let's head back to the slides to see what's next. All right. Hey, with that last example, we did see some pretty cool stuff. We saw how it kind of reminded us of a geometric series. We know convergence of geometric series. And we were able to even use the sum formula for a convergent geometric series to have an idea of what function that power series represents. It's pretty cool stuff. We are going to call the set on which a power series converges, so all values of x, for which we'd get a series of constants that converges. We're going to call that set for which a power series converges its convergence set. Or we could call it its interval of convergence. So first note, convergence set is the exact same thing as interval of convergence, which is also the exact same thing as domain. We can use these three terms interchangeably. Now I'm probably going to use interval of convergence most often, followed by domain. I use domain and interval of convergence interchangeably. I rarely use the phrase convergence set. Now the domain, or if you prefer the interval of convergence, they mean the same thing. It can take one of three forms, and this is true for every power series. The domain will take one of three forms. And to make sense of this, I'm going to head back to the chalkboard. All right, folks, just left off where I said that the domain or interval of convergence of a power series can take one of three forms. So let me put down those three forms. So this is every power series. The domain is going to be one of the following three forms. The first form, The domain is nothing more than a single point. I mean, if your power series is centered at C, the only value of x for which the power series converges is the number C. We're not going to see too many of those because those aren't exciting. They're kind of boring. The domain could be an interval. So let me make a number line here. Let me get C on here again. So when I say an interval, I'm talking about an interval around C. An interval where C is like the midpoint of the interval. So let me just arbitrarily say that this distance is uppercase R, which means that distance is also an uppercase R. So my interval here, if I'm at C and I go to the right R units, I'm at C plus R. If I'm at C and I come R units to the left, that's C minus R. So my intervals goes from C minus R to C plus R. And for all values of x, anything that you pick in that interval, the series converges. The power series converges. Well, the third form that the domain can take is that, well, I'll just abbreviate it all down to just say all reals. The power series converges for every real value x. So again, number line. My power series is centered at C. To say it converges for all reals, the domain is all reals. The interval of convergence is all reals. Well, it would be the entire real number line, which we know you can write that as negative infinity to infinity. Okay. Make sure you have this in your notes because I'm using each one of these parts to write the following theorem. So let's get this theorem on the board. So this theorem, so I'll start off by saying for a power series centered at C, and parenthetically, I'm just reminding you that a power series centered at C looks like that. One of the following is true. Number one, the series converges only for a single value, x equals C. So notice how I'm matching number one. I'm matching it up with number one. Two. Well, there's more words here to match up with number two over there. So let's get these words down. There exists a real number R. R is greater than 0, such that the series converges absolutely. The most exciting type of convergence. It converges absolutely for, okay, now to make sense out of what I'm about to write down, because number two matches up with number two, keep in mind this picture saying for all values of x, for any x that you pick inside the interval, the power series converges. Well, For any x inside the interval, so let me try to just kind of squeeze this in right here off to the side. For any x that's in the interval, c minus r to c plus r, I could write it like this. C minus r is less than x is less than c plus r. That's saying x has to be trapped in here. From this compound inequality, I could subtract c from each piece to get negative r is less than x minus c is less than positive r. And then this compound inequality matches up exactly with the absolute value of x minus c less than r. I mean, when you see an absolute value inequality, this is how you would rewrite it. So it's a two-way street. And that's how this theorem continues. There exists a real number r greater than 0, such that the series converges absolutely for absolute value of x minus c less than r. That's how we represent being in this interval. And it diverges. Well, it diverges if you're outside of the interval. So being outside of the interval means absolute value of x minus c is greater than r. And then number 3, if it converges for all reals, well, number 3, the series converges for all reals. Okay. All right, folks, there's a little bit more to this theorem. There's a little bit more where I have to introduce some vocabulary. So I have to go over here. I have to erase this, but hopefully you have this in the notes because I'm going to keep referring back to this as I continue the theorem. So, continuing this theorem, this r, it has a name. It's called the radius of convergence. So for each of these 3 parts, 1, 2, and 3, for number 1, well, if the series converges only at a single value of x, that means, you know, I see where my x equals c. Look at that picture. If I don't move to the right any and I don't move to the left any, that means r has a value of 0. That's what it means for a single value of x. The radius of convergence is 0. For number 2, well, the radius of convergence r is equal to r. Now you see why I picked the number r, or the variable r initially. It was setting up radius of convergence. And then for number 3, well, if you converge for all reals, it doesn't matter where you are centered. The radius of convergence is infinity. So I have to add one more thing here. And I mean, this is kind of like the end of the theorem, but I'm going to add one more thing. You know, again, we're going to be interested in finding the interval of convergence, the domain of the function. The interval of convergence is all x for which the series converges. It will be all values of x. We can't get the interval of convergence without knowing the radius of convergence. So let's head on back to the slides. I bet we're going to look at an example where in this first example we're just going to find the radius of convergence. But that's not what our game plan is. That's not what the big deal is. The big deal is to eventually come up with the interval of convergence. So this first example, We're just going to find the radius of convergence because it's necessary to get the radius of convergence in order to determine the interval of convergence. So let's head back to the slides and see what's next. All right, we did a lot of stuff at the chalkboard. We saw the 3 forms the domain could take, and I ended up putting that into a theorem. You learned about something called the radius of convergence, and how, well, we're going to see how that's going to be instrumental in helping us find the interval of convergence. But folks, before we start finding an interval of convergence or a domain, we need to first practice finding the radius of convergence. The radius of convergence is necessary in order for us to find the interval of convergence or the domain. And an old dear friend of ours, the ratio test, is going to be very, very helpful in this endeavor. So let's determine the radius of convergence for the series n equals 1 to infinity, x to the n over n times 3 to the n. So I'm going to head off to the chalkboard. Make sure you have this example written down. I'm heading off to the chalkboard to work through this example. All right, this example, we're asked to find the radius of convergence for the series n equals 1 to infinity, x to the n over n times 3 to the n. The first thing I'll just kind of make a quick note of is, where's this power series centered? Remember that general form was parentheses x minus c to the n power. Well, it looks like if that x minus c to the n power is just simply written as x to the n, it looks to me like c has a value of 0. So our power series, this power series, is centered at 0. All right. Like I told you this is the truth. Our very, very good friend in doing these problems, coming up with the radius of convergence, which then will help us determine the interval of convergence. Our near dear friend is the ratio test. So remember the ratio test. P, we define P to be the limit as n goes to infinity, absolute value a sub n plus 1 over a sub n. And so for this one, that gives us the limit as n goes to infinity, absolute value, all right, a sub n plus 1. That would be x to the n plus 1 over n plus 1 times 3 to the n plus 1. And you remember from the ratio test, I don't do divided by a sub n, divide by a sub n. I turn it into multiplying by the reciprocal. So n, 3 to the n over x to the n. And yes, I'm going to rewrite the stuff inside the absolute value, get kind of all the like parts together as fractions. So I have an x to the n plus 1 over x to the n. I have a 3 to the n over 3 to the n plus 1. And then I'm left with an n over n plus 1. So simplifying, x to the n plus 1 over x to the n. Well, that just simplifies to x. 3 to the n over 3 to the n plus 1. That simplifies to 1/3. Keep in mind, as n goes to infinity, x is x. As n goes to infinity, 1/3 is 1/3. It's only this part right here now that has n's involved. And in looking at this piece, I'm going to do another step. So I'm doing a couple of steps at once here. Simplifying. I'm going to divide everything in the numerator and everything in the denominator by n. So that I can now do the limit. See, the limit as n goes to infinity. Well, I just said that's x, that's 1/3. It's this piece right here. I'd have a 1 over 1 plus 0. 1 over 1 plus 0, that's 1 over 1, which is 1. So this limit is the absolute value of just x over 3. Folks, that's what p is equal to. Remember, we defined p to be this mess. So we know, and I'm going to pull it up here, we know p is the absolute value of x over 3. And what do we know from the ratio test? When do we have absolute convergence? That's right, we have absolute convergence when p is less than 1. Well, if p is absolute value of x over 3, that gives us, we have convergence when absolute value of x over 3 is less than 1. Absolute value inequality, we immediately rewrite it as the compound inequality. -1 less than x over 3 less than 1. And then we multiply everything by 3 to get this. That tells me my radius of convergence is 3 because I'm centered at 0. That's why I made this a note initially. I'm centered at 0. For any x's from -3 to 3, that tells me my radius of convergence is 3. And I also know right now, if I pick any x inside the interval, my original power series converges. But let me make this note. This right here tells me that my radius of convergence is 3. And as long as I pick any x inside the interval, the power series converges. But look at the endpoints. Look at the endpoints of -3 and 3. If you put -3 in here for x, if you put -3 back into the original power series for x, and you crank it through the ratio test, -3 would be in here for the x. That's the absolute value of -1, which is 1. Remember, the ratio test is inconclusive if p equals 1. So if -3 were in place of x all the way through, you're going to end up with p equaling 1, inconclusive. Likewise, if you put 3 in for the x, well, 3 over 3 is 1, you get p to be 1. The ratio test is inconclusive. So while I could say this is the radius of convergence, I can say that power series converges for all x inside this interval. I don't know what's happening at -3. I don't know what's happening at 3 because my ratio test is inconclusive. And on that note, let's head back to the slides and see what is next. All right, so in that last example, we saw the radius of convergence was 3. We knew the power series was centered at 0, so we have the radius of convergence is 3. So we know any value of x inside the interval, -3 to 3, any x you pick inside the interval, -3 to 3, would give a series of constants that converges. But we also saw that at the endpoints, at -3 and at 3, the endpoints of the interval, the ratio test was inconclusive. Remember, the ratio test is inconclusive if p is equal to 1. Well, again, in our last example, I showed that the endpoints of the interval at -3 and 3, the ratio test would be inconclusive. So we have a problem at the endpoints. We know that that power series in the last example converges for any value of x inside the interval -3 to 3. We don't know what's happening at the endpoints. So here's the deal. Once we know the radius of convergence, that gives us an interval. It gives us an interval that we know the power series converges for all x in the interval. We just don't know what is happening at the endpoints. So what we have to do, we have to check the endpoints separately. We have to take those values of x at the endpoints of the interval, toss those values of x into the power series. That will create a series of constants. And we learned so many techniques in the prior chapter on analyzing when series of constants converge. That will give us the interval of convergence. So folks, let's continue that last example. Let's get the interval of convergence, also known as the domain, of that series that we did in the last example. So I'm going to head off to the chalkboard. I'm going to pick up with us knowing the radius of convergence was 3, and it gives us the interval -3 to 3. And we're going to crank through, just checking the endpoints. All right, folks, this example, we were asked to determine the interval of convergence for the series n equals 1 to infinity x to the n over n times 3 to the n. So in our last example, we determined the radius of convergence for this series. We found the radius of convergence was 3, and since it's centered at 0, that gave us the interval -3 to 3. But as we just discussed in that last example, the ratio test is inconclusive at the endpoints. It's inconclusive at x is -3 and at x equals 3. It's inconclusive because at -3 and at 3, that p, which is what's defined from the ratio test, ends up being a value of 1. And our ratio test says inconclusive if p is equal to 1. But we need to determine the interval of convergence. And this is what you have to do. This is the process. To get the interval of convergence, also known as domain, we must check what's happening, the convergence, at each endpoint. So we have to check them separately. So what does that mean? You have to take those values of x, the endpoints of the interval, and you have to take those values of x, toss them back into the power series for x, and see what you end up with. So here I go. I'm checking the endpoint x equals 3. That gives me the series n equals 1 to infinity. 3 to the n over n times 3 to the n. Well, 3 to the n over n times 3 to the n. The 3 to the n's would cancel out, which gives you 1 over n. What do you know about that series, 1 over n? That's right. It diverges. Why? Because it's the harmonic series. Okay, so we still need to check the endpoint -3. So when we check the endpoint -3, we put -3 in for the x. And just a little bit of rewriting. -3 to the n. Well, remember -3. -3 can be rewritten as -1 times 3. So we'd have -1 times 3 to the n power. Rule of exponents says that's -1 to the n times 3 to the n. Well, negative 1 to the n times 3 to the n over n times 3 to the n. 3 to the n's cancel out. So you have negative 1 to the n over n. What do you know about that series? That's right. It converges. It converges because it's the alternating harmonic series. So we knew the interval of convergence from our prior example and knowing what the radius of convergence was. We knew that the interval of convergence was negative 3 to 3, but we didn't know, just knowing the radius of convergence, we didn't know if the negative 3 was included in the domain or if not included. We didn't know if the 3 was included in the domain or not included. So we had to check, and you have to do this, you have to check the endpoints separately. So when we checked the endpoint x equals 3, put 3 in for the x, it gave us the divergent harmonic series. So don't include the 3 because domain is where does it converge? When we tested negative 3, we got the convergent harmonic series. Square bracket. So for the power series, x to the n over n times 3 to the n, this is the interval of convergence. This tells you all values of x for which that series converges. This tells you you pick any x, including negative 3, but don't include 3, any x in that interval, toss it in there for the x, you end up with a series of constants that converges. Likewise, pick a number that's not in this interval, like 18. 18 is not in the interval. You put 18 in there for the x, you come up with a series of constants that would diverge. So interval of convergence tells you all values of x for which the original power series would converge. So let's head on back to the slides and see what's next. All right, so we saw in that last example, checking the endpoints, we saw how knowing the harmonic series diverges was important, and knowing, like the alternating harmonic series, converges. That was important. So here's where we're at. We can see that we use the ratio test to help us find the radius of convergence. That gives us an interval for values of x for which the power series converges. But to get the interval of convergence, the endpoints of the interval given by the radius of convergence, we have to check them separately. And again, these endpoints must be checked separately because at the endpoints, the ratio test is inconclusive. So let's do a couple more examples where now this is like the real deal, folks. Getting the interval of convergence. That's what we are interested in because it's the domain of the function. So let's find the interval of convergence for these two power series. So make sure you write these down in your notes because, I'm heading off to the chalkboard to work through them. All right, this example, you had two parts, part A and part B. Determine the interval of convergence. The first one was the series n equals 0 to infinity 4x to the n. The first thing I make a note of is I note that it's centered at 0. The second thing I kind of make a note of is this series is the same thing as the series 4 to the n, x to the n. All right, let's crank it through the ratio test. So let's see, a sub n plus 1. That would be 4 to the n plus 1, x to the n plus 1, over a sub n, which is 4 to the n, x to the n. And Here this doesn't look too bad. I think I can just simplify this without splitting it into separate fractions. 4 to the n plus 1 over 4 to the n. That simplifies to 4. X to the n plus 1 over x to the n simplifies to, well, just x. So the limit as n goes to infinity of absolute value of 4x. It's just absolute value of 4x. So folks, that's what P is. Remember the ratio test. You have convergence when P is less than 1. So here, since P is absolute value of 4x, you have convergence when absolute value of 4x is less than 1, which you rewrite as -1 less than 4x less than 1. Divide everything by 4. You get -1/4 less than x less than 1/4. So right now I know the radius of convergence is 1/4, but you know what? I need to know the interval of convergence. And here's one quick little check to make sure I'm on the right path. Where your power series is centered, better be the midpoint of this interval. And 0 is the midpoint of -1/4 and 1/4. All right, so we need to check the endpoints. We need to determine the interval of convergence, so we need to check the endpoints of this interval. So let's check the 1/4. So 1/4 comes in for x. So you get the series of 4 times 1/4 to the n, which is the series 1 to the n. Converge or diverge? That's an easy one. Diverges. Why? The nth term test. That was a very friendly one. Now we check -1/4. Well, that gives us the series 4 times -1/4 to the n, which is the same as, what, -1 to the n. Does that diverge or converge? It diverges because it's the nth term test. These were two very quick, friendly endpoints for this one. So we know not to include either endpoint. Therefore, our interval of convergence is -1/4, 1/4. Okay, before we look at part B, when you start to get enough experience working with power series, and you see the series 4x to the n. So when you get enough experience, you might start to say, gee, that looks like a geometric series where r is 4x. And you know with the geometric series, so it looks like a geometric series where r is 4x, and you know you have convergence when absolute value of r is less than 1, when absolute value of 4x is less than 1, and the geometric series test also tells you about these endpoints. Because the geometric series test says you have convergence when you're less than 1. If you're greater than or equal to 1, it diverges. So right here, you would be done knowing the interval of convergence is -1/4 to 1/4. But you got to work with these. You have to do a lot of work with power series to start to get that kind of insight. So I want you to focus on how we did the last example, how we did this one. You need to use your near dear friend, the ratio test. And Oh, with that said, there was a part B to this example. Let's check out part B. So bear with me as I do some erasing here. Let's see, part B. So part B was the series. N equals 0 to infinity. X minus 1 to the n over n plus 1 quantity squared. The first thing I notice, the first thing I make note of, this power series is centered at 1. X minus c to the n, so it's centered at 1. All right, let's go through and do the ratio test. So the ratio test, the limit as n goes to infinity. So let's see, a sub n plus 1, that would be x minus 1 to the n plus 1 over n plus 1, so that's an n plus 2 quantity squared. Divided by a sub n, so times the reciprocal. So we have the limit as n goes to infinity. Let's see. Okay, I'll write it. X minus 1 to the n plus 1 over x minus 1 to the n times n plus 1 squared over n plus 2 quantity squared. Now let's see what we can do now. Well, x minus 1 to the n plus 1 divided by x minus 1 to the n, that simplifies to just x minus 1. What do I want to do with this fraction? I'm going to use a rule of exponents, and I'm going to rewrite this as n plus 1 over n plus 2 quantity squared. Then I can come inside the parentheses, divide everything in the numerator by n, divide everything in the denominator by n, and the limit as n goes to infinity of this mess, well, that's 0, that's 0. You have a 1 over 1. 1 squared is 1. So the limit as n goes to infinity is absolute value of x minus 1. Keep in mind that is p. That's what p is. I just strung it all the way down here. So I'm going to have to pull this up here now. Remember, you have convergence. Using the ratio test, you have convergence when p is less than 1. So p was the absolute value of x minus 1. Write your compound inequality. And we were centered at c equals 1, right? Yeah, 1 is the midpoint of that interval. So at least I'm going down a reasonable path. Now I need to check the endpoints separately. So check x equals 0. So you put 0 in to the original power series. So that gives you a negative 1 to the n over n plus 1 squared. And does that converge or diverge? Well, I'm going to say it converges. And it converges because, and I'm not going to write all this down, but you should check it. This is an alternating series. So when I crank it through the two key parts of the alternating series test, that's how I know that converges. It's the alternating series test. Now when I check x equals 2, so I put 2 back in for x, 2 minus 1 is 1, 1 to the n power, well 1 to the n power is just 1. So I have 1 over the quantity n plus 1 squared. Does that converge or diverge? Again, I'm going to say it converges. I'm going to leave it up to you to verify why. I'm going to mention one of two ways, and you should check this. I would compare it to the series 1 over n squared. Either a limit comparison test to that series or a direct comparison test to that series. So it converges either a direct comparison test or a limit comparison test to the known convergent p series 1 over n squared. See why we learned all those tests back in chapter 10? They're used to finish off one of these interval of convergence problems. But we now know our interval of convergence is the interval 0 to 2, square bracket around both. So, I want you to practice a couple. And let me see, make sure. Sorry to disappear on you. I'm back. From the supplement that I've posted, because I didn't feel like for this stuff right now we're doing, the book had enough problems for you to practice. So I put a supplement. So this is the section 11.2. It's supplement 1 for section 11.2. So supplement 1 for section 11.2. Right now I would like you to do numbers 1 and 7. So you know the drill. Pause the video. Do number 1 and number 7. Once you've done them, restart the video, and I'll be here at the board cranking through the solutions. Okay, number 1, you were asked to determine the interval of convergence for the series x over 4 to the n power. And I went ahead and took the liberty to rewrite that as x to the n over 4 to the n. And I would also make note, before I get started any further, it's centered at 0. So here we go. Cranking it through the ratio test. A sub n plus 1, that's x to the n plus 1 over 4 to the n plus 1, divided by a sub n. So multiply by the reciprocal. And, we know x to the n plus 1 over x to the n. We should know that's going to simplify to x. And we should know 4 to the n over 4 to the n plus 1 is going to simplify to 1/4. So the limit as n goes to infinity of absolute value of x times 1/4 is just the absolute value of x over 4. That's what p is equal to. And then again, we know with the ratio test we have absolute convergence when p is less than 1. Since p is absolute value of x over 4, we have this, which we rewrite as a compound inequality, which we then say, let me just pull this right here. Multiply everything by 4, you get negative 4 is less than x is less than 4. And quick check, we said it was centered at 0. 0 is the center of that interval. So we don't know the interval of convergence yet. We have to go check the endpoints. So we have to check. Let's check x is negative 4. So that gives us the series, well look, negative 4 over 4. What's negative 4 over 4? That's right, negative 1. You should know quickly. That diverges. Thanks to the nth term test. You check x equals 4. So you put 4 in for the x, it gives you the series 1 to the n, or just 1. You know that diverges. The nth term test. So your interval of convergence, -4 to 4, parentheses around both. Okay, now, did anyone notice from the get-go that was like a geometric series? If you did, great. If you didn't, that's fine as well. Ratio test is our near dear friend. One more I asked you to do, that was number 7. So bear with me as I, erase the board and write number 7 up here so we can crank through it. See what the deal is. Number 7, you had the series of -1 to the n plus 1. X minus 4 to the n all over n times 9 to the n. So hey, first note, we're centered at 4. All right, let's crank this through the ratio test. P equals the limit as n heads off to infinity, absolute value. All right, a sub n plus 1. Okay, first note, I'm not worried about putting any of this -1 to the n plus 1 or n plus 2 or whatever in here because it's going to be inside absolute values. So for those values of n where -1 to the n plus 1 would be negative, because it's in an absolute value, we know the absolute value of a negative is positive. So I'm not going to worry about it because it's inside absolute values. So again, a sub n plus 1, that will give us x minus 4 to the n plus 1 over n plus 1 times 9 to the n plus 1. Then divided by a sub n, so that's times n 9 to the n over x minus 4 to the n. And this one, just to help me keep my work straight, I'm going to rewrite it as x minus 4 to the n plus 1 over x minus 4 to the n times 9 to the n over 9 to the n plus 1 times n over n plus 1. All right, let's see what we can simplify. Well, x minus 4 to the n plus 1 over x minus 4 to the n, that simplifies to just an x minus 4. 9 to the n over 9 to the n plus 1, well, that simplifies to a 1/9, so that's looking pretty good. Looking ahead to this fraction, since we're doing the limit as n goes to infinity, all of this is just going to be coming along for the ride. This is the only piece that involves n's. So I'm going to divide everything in the numerator and the denominator by n so that I can now do the limit. See, the limit as n goes to infinity, I'm going to have absolute value of x minus 4 times 1/9. And then this piece here, well, that would be 0. 1 over 1 is 1, so that's what the limit is. So P, remember P is this. Yes, you have convergence when P is less than 1. So that's absolute value of x minus 4 over 9 less than 1. That's -1 less than x minus 4 over 9 less than +1. Sorry to keep tagging this along. Multiply everything by 9. So we have a -9 less than x minus 4 less than 9. And add 4 to everything. -5 less than x less than 13. Wow, so we said we were centered at 4, so that would be my question. Is 4 the center of the interval -5 to 13? Yeah, yes it is. In fact, the radius of convergence ended up being 9. All right, so continuing on, we've got to check the endpoints. So here we are, checking the endpoint -5. So -5 goes in to the original series. So -5 goes in for the x. So you'd have -5 minus 4. That's -9. And you know what? I gotta rewrite this. -9 is that's -1 times 9. So we'd have -1 times 9 to the nth power. So that's a -1 to the n, 9 to the n. Okay, some neat stuff happening here. The 9 to the n's cancel out. Bases are the same and you're multiplying, so you add those exponents. So we simplify this down to -1 to the 2n plus 1 over n. So when we put -5 in for the x, it's simplified down to this. And we have to ask ourselves, does it converge or does it diverge? And why? Well, the first thing, this is not an alternating series. As you put in values for n, this exponent, 2 to the n plus 1, it is always going to be an odd number. For any value of n, that's an odd number. And because it's an odd number, -1 to an odd number, so -1 to an odd power is always -1. So really this series is nothing more than the series -1 over n. I know this diverges. How do I know it diverges? It's nothing more than -1 times the known divergent harmonic series. Diverges. Oh, but we better check 13. So we put 13 back in for the x into the original power series. So you'd have 13 minus 4 is 9. And let's see, we know this series, well, the 9 to the n's cancel out, so you have series -1 to the n plus 1 over n. I know this series converges because it is alternating. In fact, it is the alternating harmonic series. So after we analyze the endpoints, we can now conclude the interval of convergence is -5, not including -5, to 13, including 13. All right, hopefully you got those two and you're starting to feel a little more comfortable with this. You're seeing your near dear friend, the ratio test, is very important. And a lot of these other tests that you learned in Chapter 10, they come out when you're analyzing the endpoints of the interval. Let's head on back to the slides for one final comment, but it's an important comment going forward. All right, folks, so we saw in the last example, when checking the endpoints, we saw how the nth term test was pretty important. We also saw remembering the alternating series test was pretty important. And, direct comparison test, limit comparison test, everything that we learned in the last chapter is really important. The couple of problems I asked you to try on your own, you saw the nth term test being pretty important, as well as the harmonic series and alternating harmonic series. So again, this highlights Everything learned in Chapter 10 comes in handy in helping us get the interval of convergence. I have a final note here. When you apply the ratio test, when you apply the ratio test, if you get P, that limit, if you get it to equal infinity, so if P equals infinity, that means the radius of convergence is 0. Well, folks, if the radius of convergence is 0, that means the power series converges only at a single value. It converges only at x equals c, where the power series is centered. If when doing the ratio test you get P to equal 0, so the limit is 0, that tells you the radius of convergence is infinity. Well, if the radius of convergence is infinity, that means your power series converges for all reals. That means its domain is negative infinity to infinity. So now, folks, this ends part 1 of the section 11.2 video. So at this time, you should do, in section 11.2, you should do the exercises 9, 11, 15 through 21 odd, 25, 29, 35, and then the supplement, because I have some supplement exercises. So it's the section 11.2 supplement 1. You should do all of those as well. So that's it. That's it for part 1 of the video. Thanks for watching.